Okay, so I'm going to go over the chapter 6, 7, and 8 recitation. So this is kind of unique because it's one of the first opportunities you've had where you don't already know if it's going to be substitution or elimination. So we broke up, substitution questions from elimination questions, SN1, SN2 we learned, and then E1, E2. But now you have to consider all the factors and decide, is this going to be SN1, SN2, E1, or E2? So, and I've already talked before, and I have other videos about sort of how I decide which one it's going to be, but I look first at the nucleophile, then I consider the substrate, and then any other reaction conditions. And then after I've decided if it's SN1, SN2, E1, or E2, then based on that mechanism, I can consider regiochemistry or stereochemistry if I need to. So that's sort of my approach. So for my first one, we have NaOH. So anytime you have a metal counterion, that's Na plus, and then the organic molecule that's next to it is going to be negatively charged. So this metal counterion, this is sodium is positive, and then this organic oxygen, the molecule that's attached to it, is going to be negative. So OH minus, that negative charge indicates it's going to be a strong nucleophile, and it is narrow, so it's going to probably favor SN2, is what I think. But you can't have a SN1, SN2, E1, E2. You have to double check what your leaving group is, if you can even have one of those. So then I'm going to look over here to my leaving group, and I do have a good leaving group. This is like a tosyl group, which is essentially just turning an alcohol into a good leaving group. So I just kind of imagine that to just be a leaving group. So we have a good leaving group, and it's a primary leaving group. So that tells me even more it's going to favor SN2. So that's what I think is going to happen, is it's going to be SN2. There's no heat, and there's nothing else that really makes me think that it would favor E2 over SN2. And it can't go E1, SN1 because it's a primary leaving group. So I'm going to stick with SN2. I'm going to attack from the backside and kick this out. So that would be the mechanism. So this goes from being a good leaving group to being OH, would be your new nucleophile. Your oxygen, these electrons right here that make this oxygen negatively charged, are what form this new bond, and this leaving group leaves. So this is our product. And so it says consider regiochemistry, and stereochemistry, rearrangement. There's no rearrangement in SN2 or in E2. Regiochemistry, we don't have to worry about because it's just going to substitute at the same carbon. And then stereochemistry would be an inversion of stereochemistry if we're at a stereocenter, but this is not a stereocenter, so we don't have to worry about that. So that would be this answer. Okay, looking at this one, again, we see that this is a metal counterion, so this would be OMe minus. This chlorine is attached to a carbon that has this carbon has one carbon. So this is a primary carbon. It has some branching next to it, or primary leaving group, I guess, not primary carbon. Primary leaving group, it has some branching adjacent to it, but it's not a tert butyl group. So there would be some hindrance, but not a ton. So I'm going to say with a strong nucleophile, that's going to favor SN2 or E2. And then with this nucleophile being narrow, it's going to favor SN2 again. It might do, I like to talk about how, this is real life in organic chemistry. You're going to get a mixture of these products always. And when I look at this and I see this branching off to the side, that tells me that we might get some E2 more probably than we were going to get here, but still the primary product I think would be SN2 because we have a narrow nucleophile and only a little bit of branching here. I think if it's a tert butyl, that would push it a lot more towards an E2 reaction, but just with a little bit of branching, just like an isopropyl, I think it's probably not too bad. So that still makes me think it's going to go E2. So then again, we have SN2, not E2. So we have our nucleophile attacks from the backside and kicks out our carbon, and our final product would look like this. If you drew it with the methyl, that's okay too. And in this case, again, we don't have to worry about regiochemistry because it's not an elimination reaction. The substitution just takes the place of the exact same leaving group, carbon where the leaving group was. And then we don't have to worry about rearrangement because there's no carbocation. Stereochemistry is inversion of stereochemistry, but this is in the stereocenter, so we don't have to worry about that. Okay, now this nucleophile, this is a neutral nucleophile, so this is going to be a weak nucleophile. So that's going to favor SN1 or E1. And then the next thing I notice is that there's heat. So heat definitely favors E1, I think. And then this leaving group is on a 1, 2, 3, a tertiary carbon. So that's going to really solidify that it's E1 for me. We have a leaving group, a good leaving group that's going to make a good carbocation. And then we have heat to favor elimination. So the leaving group is going to leave, and we will be left with a carbocation like this. Now we can choose from one of these 1, 2, 3 beta carbons. So let me get another pen color. Oh, here, this one will be good. So you can look at this carbon, or this carbon. I think it's useful to show you all the products so that you can see which one is more substituted. So if we took from this hydrogen right here, let's say your weak nucleophile took that hydrogen there, and then these electrons filled in, this product would look like this. And then if we took from one of these hydrogens over here, well, too late, I committed to the red. If we took from one of those hydrogens, this hydrogen, actually, no, I will do it in a different color. Let's see. Here's black. Okay. This hydrogen and this hydrogen, they would actually end up giving you the same product. If you're not sure why that is, you can pause it and try taking from both of those hydrogens. That's a good practice. But if we took this hydrogen and the electrons filled in, you'd get the same product from either one of these. Then your final product would look like this. So this would be if you took one of the black hydrogens, and this would be if you took one of the red hydrogens. So if you look between these two, and you're trying to figure out which one is more stable, which one's more substituted, to say if what the regiochemistry is. And I forgot to check for rearrangement. So I'm going to go back and look at this, and it says, predict the products considering regiochemistry, stereochemistry, and rearrangement where appropriate. So regiochemistry, we're about to talk about that with these. Stereochemistry, we don't have to have any special stereochemistry considerations because it's E1, so we get that carbocation, so it's flat, so we don't have to worry about that. And then in the rearrangement, this is already the most stable carbon around, so we didn't have to worry about rearrangement. I should have gone through all those steps with you. Sorry, I kind of glossed over some of them. So now you have these two possible products, and you're trying to tell which one is Zaitsev and which one is Hofmann, and then which one does this nucleophile favor. Well, when I look at this, I see one hydrogen here, and when I look at this, I see two hydrogens here. So this is tri-substituted, and this is di-substituted. So the more substituted is the more stable is the Zaitsev, and the less substituted is the Hofmann. And the more stable, more substituted one would be favored by a narrow nucleophile, and this is a narrow nucleophile. Nucleophile being like small or narrow is really about branching. So, OH minus, or if we're looking for a weak nucleophile, water is a smaller one. But then, if we have some carbons, this has some hydrogen around it. So these two are somewhat weak, ethyl or methyl off of it. There's a little bit of branching around it, but not a ton. I mean, the carbons aren't branching. But then we start to get into bulkiness as we start to get into isopropyl groups. This is more branching, more electron density close to the nucleophile than a straight chain or water. And then they're really this is definitely bulky, this is going to be significantly affected, is tert-butyl. So it's sort of a spectrum where water or OH minus, and then, methyl or ethyl, where it's kind of a straight chain. Even if this chain was longer, We care mostly about the branching right there nearby the nucleophilic atom. Really, if it's like primary, that's narrow. If it starts to be secondary or tertiary, that's when it starts to get into bulky territory. And I will say that this is like, I think isopropyl is kind of a gray area. And I think that we should embrace the gray areas in organic chemistry because in reality, you are going to get a mixture. And so I want to spend time acknowledging that. Sometimes I think we teach it like, and this is the one right answer, but there's not always one really clear right answer. There are times I'm not sure or I'm not confident, even though I've been doing this for a really long time. So yeah, I think that that's important, and I think it's good to talk about. But in this case, I would say that your predominant product from this is a smaller nucleophile. There's not a lot of branching. Your nucleophilic atom is primary, and that tells me that site-Ceph product would be favored. So this would be the major product. You would probably get still some Hofmann product, and you'd probably also get some of the substitution product, but this would definitely be the one that's favored. Okay, this next one, I see CH3O and then Na. So this is CH3O minus essentially. So this is negative. So that's a strong nucleophile. So when I think about my chart, strong nucleophile favors SN2 or E2. And then I consider other reaction conditions. This reaction condition is heat, so that favors E2. And then let's look at our leaving group. We have a good leaving group, and it is secondary, so that is good for E2. So I think this is going to be an E2 reaction. So then we do have to consider, again, regiochemistry, but we also have to consider stereochemistry. So if we know that it's E2, we have to consider regiochemistry. Is it site-Ceph versus Hofmann? And in this case, I think it is going to be site-Ceph for the same reason I talked about last time. This is pretty narrow, so you're going to get the more substituted product, if possible. Sometimes it's not possible. And then stereochemistry, it needs to be anti. We need to make sure our hydrogen and our leaving group, our hydrogen that gets stolen and our leaving group are opposite from one another. And then there's no rearrangement in an E2, so we don't have to worry about that. So these are the things we have to look at. So I find this to be easiest just to be to draw a Newman projection. So you have a bromine that would be on your right, and the hydrogen going into the plane of the page would be on your left if you're looking at it from this angle. And then in the back, you have your ethyl, and then on your right, a CH3, and then going into the plane of the page, a hydrogen. So those are already opposite from each other. So your alkene would look like this. And that means that there is a possibility for it to go in between the more substituted side. So that's why I chose between these two carbons, is because that gives you the more substituted. There's a hydrogen there that it can take that'd be more substituted. And then this shows us sort of the structure of our, I just realized I needed to have one more line on this right there. So that's an ethyl group straight up, not a methyl. So that's my bad. So this sort of shows you the structure of our alkene. Now, my PLTL leader showed me kind of a cool trick, whereas if this is a wedge and this is a dash, then you can that these two groups are going to be opposite of each other. That's kind of harder for me to see. Actually, it's easier for me to see the Newman projection, but there is some risk involved in that. Like you just saw, I misdrew my Newman projection right here, and so I almost missed and got the wrong answer here. So you have to really make sure that you're considering double check yourself and make sure that whatever way that you can consistently get right works. And so what I did to actually catch my mistake is I saw what I had written here, and I looked back over here and was like, oh yeah, these two would be on the opposite each other because this is already anti. And then I was like, wait, I don't have two ethyl groups. So it's always worthwhile to go back and double check yourself. Okay. Sorry if you can just hear that in the background. It's my husband making noise. He's making dinner for us. So sweet. All right, so this is a strong nucleophile. So that would favor SN2 or E2. And then I also noticed that this is a bulky nucleophile. So because this is a bulky nucleophile, I actually think this is probably going to favor E2 over SN2. And again, this is a primary leaving group. This carbon is only attached to one other carbon, but it has branching nearby. So the branching of this with the branching of this really kind of solidifies me in my thought process that this would favor E2 over SN2. I think it's unlikely to go SN2 with this much steric hindrance. So I think that this would favor E2. So if we look at our carbon, our alpha carbon right here, there's only one beta carbon, one adjacent carbon, and that has one hydrogen. We weren't given stereochemistry, so we don't have to worry about stereochemistry, and we don't have to worry about regiochemistry because there's only one option for the adjacent hydrogen. So this would take here, fill in here, and your leaving group would leave, and your final answer would be, oh, I'm so bad at drawing 7-membered rings. Let's see if I can do it. Is that it? 1, 2, 3, 4, 5, 6, 7. Did it. Nice. This would be your final answer with the alkene off the 7-membered ring. So that's kind of how I approach these questions is first I decide is it SN1, SN2, E1, E2. Then I draw the mechanism and consider the regiochemistry and the stereochemistry. Oh, but we have more. So I don't know what I was talking about, like we were wrapping up. Okay, so the next one, NaOET. So this is OET minus. So, oh, you can't even see it on here. OET minus. So this is going to be a strong nucleophile. It's going to favor SN2 or E2. And then looking at this, this carbon this is a secondary leaving group. So it can go SN1, it can go SN2 or E2. There's no heat. Honestly, I think that this would favor SN2. It's not impossible, though. It could give you some E2 as well. And again, I think this is one of those gray areas where you're going to get some E2 for sure, more than you might if it wasn't this secondary, but it can go SN2, and I think it's going to prefer to do that. And so we need to consider stereochemistry and regiochemistry. Stereochemistry on this one is going to be harder to see because we need to get inversion of stereochemistry, and this is in the plane of the page, and it's going to attack from the other side. So I'm actually going to rotate this one to make it a little bit easier to see for myself, because I could draw the major group on this side, but I think that would just be a little bit harder to see. So what I'm going to actually do is put my leaving group, I'm going to rotate this, let's see. I want my hydrogen facing forward. So I'm going to make my hydrogen point up. And then my bromine that was pointed up is going to point back. And then my CH3 that was pointed back is going to point forward. So I rotated that one sort of unit so that then when I get my backside attack here, it comes in and attacks on this carbon. And then this leaving group will leave. And as this is attacking, it's going to push this. It's attacking from the side with the CH3. It doesn't matter where you draw the curved arrow. So it just needs to be pointed to this carbon. But I've seen some people draw it to help them visualize it, draw it like from where the leaving nucleophile actually attacks from. But we don't actually worry about that too much. As long as it's pointed to the carbon, but know that the stereochemistry gets inverted. So now your OET is going to be, or your ethyl is going to be a wedge, and your CH3 is a dash, and your hydrogen is still in the plane of the page. And we don't have to worry about regiochemistry or rearrangement with an SN2. Okay, again, we have NaOH. Wow, I really favored SN2 on this one. OH minus SN2, because it's a strong, it's negative, so that equals strong. So that's going to favor SN2 or E2. Again, we have a secondary leaving group, which could go either way, but with a pretty narrow nucleophile, I think it would favor SN2. And again, it's pointed up, so I'm going to rotate this again. Let's see. And we have, I'm going to make my bromine point back again. I'm going to make my hydrogen move forward and my CH3 go up. So CH3 goes up, bromine's down, and hydrogen's forward. So my OH minus is going to attack from this side and kick this bromine out, and you end up with an OH here, and then a hydrogen pointed back into the plane of the page, and your CH3 hasn't changed. And notice this other CH3 over here hasn't changed either. And sometimes I see that, especially on like standardized tests, that it's almost like a trick that like they change this and they shouldn't. The stereochemistry doesn't change here. So make sure that the stereochemistry is only changing at your carbon of interest. Okay, so this is a weak nucleophile, water. So that means it's going to favor SN1 or E1. Our leaving group is tertiary. So that is, again, a good sign for SN1 or E1. There is no heat, and this is a narrow nucleophile. So I think this is going to favor SN1 over E1. So the leaving group leaves, and you get a carbocation. Looks something like this. We have a narrow nucleophile, so that's going to favor Site-Sef. Site-Sef? I always spell this wrong. Site-Sef. Site-Sef. Something like that. It's also, you can spell it with a Z. Anyway. And we also, anytime we see a carbocation, that should be like a little red flag, like, oh no, stop, or a stop sign. Oh no, stop, there's a carbocation. Does it need to rearrange? In this case, it doesn't, because it's tertiary, and if it moved over, it'd be secondary, so it's happy here. And now our nucleophile will attack. This is not a chiral center, so we don't have to worry about stereochem. I don't know why I talked about Site-Sef, because this is not an E1. It's SN1. So just don't mind me. I'm a little all over the place. Okay, so this water will attack this carbocation, and there's no rearrangement, and we don't have to worry about regiochemistry because it's SN1, and we don't have to worry about stereochemistry because it's not a chiral center, and so our product looks like this. Our water attacked. There's still a negative charge here, and this is positive. There's still a lone pair here, and this is positive, and so we'd have to have a deprotonation step. Probably the water would grab it, but as long as you know that the proton gets lost, then this is your final answer. Okay, this is when I first see this, there's not a clear nucleophile here. And so then I go back to what else have we learned, and the only other reaction that we've learned at this point is acid-base. And I see that there's an alcohol here and a relatively strong acid here, so I'm going to guess that an acid-base reaction is going to happen first. I'm actually going to show you how the structure of H2SO4 looks. H2SO4 looks like this. If you want, sometimes people just put like HA like for the rest of the acid, but this is the reaction that happens. Is this acid-base reaction will favor the weaker acid forming. So this alcohol will get protonated, and this leaves that behind. And so you get HSO4 instead of H2SO4, HSO4 minus. Is this gains that negative charge. Looks like this. O minus, and then this side is still OH. So that's what you end up with, HSO4 minus plus a protonated alcohol. And we know that this side of the reaction is favored because the pKa of this is like, oh shoot, what is it? Probably around like -1-ish. And the pKa of this is like way more. -1, way more acidic. -1, honestly, I don't know. I'm going to go check real quick. A quick Google told me it's -3. So this one is definitely weaker. So this one is going to be the favored one. And then that means that we now have a good leaving group and we have a good nucleophile. It's the pKa of the second one is 1 point something. if we lose this other hydrogen. So this is still it's not like the strongest base. And we know that in general, in acid catalyzed dehydration, secondary alcohols are going to undergo a E1 where the leaving group leaves. So the leaving group is going to leave in this case. And you'll get a positive charge. And then that is going to undergo rearrangement. We always have to consider rearrangement when we see a carbocation. So the hydrogen here shifts to fill in there to get a rearrangement from a secondary carbocation to a tertiary carbocation that's more stable. And then this is it's not the most narrow, but I think in general, acid catalyzed dehydration favors the more substituted. So I think that this would be the product that you would tend to get. I think it would look like this. But I wouldn't go. I could see why with H2SO4 you might think that this is kind of bulky and so it might favor Hoffman. I think that I could go either way on that. So I don't feel 100% confident one way or the other. I think that it would still favor, because the water that this would have to be dissolved in to go in solution would likely be your nucleophile. So I actually think it would favor Site-Ceph over Hoffman. So I think this would be your answer, because to have H2SO4, you also need water. So I think that would be why it would favor Site-Ceph. Okay, next one. This is the same type of question. The first thing I see is there's not a clear nucleophile, but we have an acid and a good enough base to undergo an acid-base reaction. And so again, this would protonate your alcohol, and you'd get A- and OH2 plus. And now this is a primary leaving group, so this cannot go by SN1 or E1. It has to go by E2. For acid catalyzed dehydration with heat, it'll be elimination, so it has to go by E2. And so because it is E2, we don't have to worry about rearrangement or anything like that. And there's only one beta hydrogen, so it can only take from here and kick this out. So your final product looks like this. Okay, the bottom one, NaOET with Cl. Okay, so this is Na plus, and this is OET minus. So this is a strong nucleophile, so this is probably going to favor SN2 or E2. There's no heat, so SN2 probably. And then I'm going to look at this leaving group as tertiary. So you cannot get an SN2 on a tertiary leaving group because you can't have that partial bond to this carbon form when there's that much electron density around it. So it's not going to go SN2 in this case. It's going to favor E2. So if it's going to favor E2, we have to consider Site-Ceph versus Hoffman, and we have to consider if it's anti-periplanar. But in this case, this isn't a chiral center, and on any of these adjacent any of these beta carbons here, we have two beta carbons, so it's going to form the more stable product if it can, so we don't have to worry about that. It's going to favor Site-Ceph, which gives you the more substituted, so that's going to be this internal one. And if you're not sure, if you look at those and you're like, why is this going to be more substituted? I encourage you to draw the product like I did for this one. Draw both of the products out and see which one is more substituted. But in this case, I can tell from looking that this one's going to end up being more substituted. Another way you can think of it is the Hoffman is the side with the more H's gets taken, and the Site-Ceph has less H's. So that might help you too. So this is going to go here and kick your leaving group out. And so we will get our double bond right here, and it'll look like this. Okay. The next question is tert butoxide. So that looks like this with K plus. K is a positive metal counterion, so whatever it's attached to is going to be negative. So this is what we're worried about. So this is going to be strong. It's going to favor SN2 or E2, but the bulkiness of it makes me think it's going to favor E2. And then I look over here, and this is another tertiary leaving group, so I'm pretty confident, again, that this is going to favor E2. But in this case, I would say because of the bulkiness, it's actually going to favor Hoffman, not Zaitsev. And so I will take one of these hydrogens. Either of these would be the same and give you the same product. If you're not sure why, you can check that out, draw one and see. But I'm going to guess it's going to take one of these hydrogens to give you a less substituted product. Because this is so bulky, it's harder to get into this more hindered side. So this tert butoxide is going to take one of those hydrogens. They're going to fill in here, and this leaving group will leave. And you end up with a alkene that looks like this, where you have double bond forms right here. Yep. And then the two hydrogens. Okay. Let's see. Activity 2, addition reactions to alkenes. Okay, so this is moving into chapter 8. So the last one, I just wanted you to practice, like, if it could be anything, SN1, SN2, E1, E2, how to approach that. But now I'm going to go through the addition, generalized addition reaction. So draw the generalized mechanism of an addition reaction. You can start with the alkene below and use E nucleophile. And there's a similar one to this in slide 15 of your notes for my students, I guess specifically in the fall of 2024, because I might have changed my notes in the future. But you should find one similar to this in your notes somewhere. So the alkene has, you can kind of almost think of this as an extra lone pair that can attack. And then this bond would break and leave that behind. So you'd end up with an addition of the electrophilic portion of this structure. And the other side where the lone pairs were, so I'm going to draw actually these lone pairs in another color. So this double bond, the pi bond here, you can think of as made up of an extra pair of electrons. And that made up this bond here. So those electrons that were there made the bond to the electron. And then this, or to the electrophilic portion. And then this nucleophile, which was neutral, it had two electrons here. And now those two electrons are solely on that nucleophile, so it's become negative. So this is a general mechanism of, I always do this. I like write out where you can draw it, and I don't. So this is the general mechanism for step 1. So this is step 1. The alkene attacks the electrophilic portion, forming a carbocation. Oh, I forgot to draw my carbocation in. Because over here, where there was one hydrogen initially, there's still only one hydrogen here. So if you do the formal charge, there's only 3 things bonded to that carbon, so this is positive. Another way you can think of it is it lost electrons, so it's positive. I was thinking of that joke, like, oh, and Adam ran into the bar and said, I think I lost my electrons. And the bartender says, are you positive? That is a joke that my cousin told me in like 10th grade, and I've never been able to forget it. I know she has a PhD too in history. Cute. Okay, so not chemistry though. Okay, so this is the first step. Alkene attacks the nucleophilic portion. It forms this carbocation and generates a negative nucleophile. Rearrangement might occur, and in this case, rearrangement does occur because this is a secondary carbocation, and if it rearranges, you can have a tertiary. So, if you have a positive charge, let's see, I'll do the hydrogen here. You can undergo a hydride shift where these electrons come and fill in, and you get a carbocation here, and your electrophilic portion still added. So rearrangement definitely did occur. Step 2 would be the nucleophile that you made in here. I'm just going to redraw it. The nucleophile will attack, and that forms the final product, which looks like this. It doesn't really matter if you draw them up or down. It's more proper to draw if you have 2 things pointed down from a carbon, 2 things pointed up. So that's why I do that. So the question is, does it make multiple products? It would. We didn't have a stereocenter, but it would make this plus an enantiomer if it's a chiral center. If chiral center. And the next question is, describe in your own words what Markov-Nikov's rule states. So Markov-Nikov's rule, basically we abided by it here just because it makes the most sense that the most stable carbocation will form. Will form preferentially in an addition reaction. So basically, when you have this electrophilic addition, it's going to add in such a way that the more stable carbocation will form. In this case, the secondary one, and then you could undergo rearrangement. So that's Markovnikov's rule. And now we're going to do this same reaction with HBr for each of these alkenes. Okay, so HBr, so in this case, the H is partially positive and the Br is partially negative. So this is the electrophilic part and this is the nucleophilic part. So these, I'll draw them in red again. These electrons from this alkene are going to attack here, and then this bond will break. So the electrons that were here, this bond is going to break and go towards your bromine. So you end up, and I like to draw in the lone pairs on my bromine just so you can see it. Bromine already started with lone pairs, right? Because of that's what the Lewis structure looks like. If you're not sure on that, you can go back to my earlier video on like lone pairs and formal charge and Lewis structures. So after that series of reactions, the more stable carbocation will form preferentially. So the hydrogen, in theory, could add to this side or this side, but if it adds to this side, you get a positive carbocation. A tertiary carbocation. If it added over here, you'd only get a secondary, and it would undergo rearrangement. So the more stable carbocation is going to form first, and that's what the electrons from this bond right here made that. And then we get a carbocation left behind, and our Br becomes negatively charged from the electrons it took on when the bond to hydrogen broke. And now this negatively charged bromine is going to come in and attack right here, and your final product will be your bromine here. And you can redraw that hydrogen if you want, but it's also implied, so you don't have to. Okay. Now for the next one, I'm not going to draw the different electrons forming because hopefully you kind of see where those come from. So the more positive, the hydrogen's going to come here because the more positive carbocation would be on the substituted position. And this also makes the Br minus, which is attacks right there, and you get Br, and that hydrogen's still there, but it's implied. And now on this one, HBr, so we get, let's see, the hydrogen would add here, so you can get a secondary carbocation that can undergo rearrangement. In theory, either one of these is secondary, but this one, being adjacent to a tertiary, can undergo rearrangement, and that means that it's the more stable option. So we get our carbocation right here, and then our Br minus that was formed in this step would attack, and you get this final product. Okay, so that's it for the chapter 6, 7, and 8 recitation. I hope that was helpful for you. Let me know if you have any questions.